NASA has discovered something incredible at the edge of the universe, and the findings are so spectacular that they could completely upend our understanding of the cosmos. From mysterious magnetic walls to enigmatic cosmic structures. Today, I'm taking you on a journey to the very limits of reality. Make sure to stick around until the end, because what you're about to see will leave you speechless. A warm welcome, everyone. The edge of the universe, a place that blows our imagination and holds the greatest mysteries of the cosmos. If you're as fascinated by these cosmic riddles as I am, then go ahead and subscribe right now. It costs nothing, you won't miss any groundbreaking discoveries, and you'll be helping me out. And if you've already subscribed, you can also really support me by giving this video a thumbs up. The YouTube algorithm loves that. Thank you so much, everyone. The cosmos keeps surprising us with phenomena that challenge even our boldest theories. And one of the biggest questions of all is probably, what is actually at the edge of the universe and beyond it? Feel free to share your theories in the comments right now. What comes after the cosmos? Nothing. Another universe. I'm really curious to hear what you think, and I'm looking forward to the discussion in the comments. So let's shed some light on the darkness and take a look at what science has now discovered at the edge of the universe. Once upon a time, 13.8 billion years ago, there was nothing yet, no planets, no galaxies, no space, no time. There was only a singularity, a point without any extension. And this tiny singularity contained the potential for an entire cosmos. You could call it the original lump. By the way, is the word Nobel actually standard German or is it Kolsch? I honestly don't know. Let me know in the comments. Anyway, this singularity suddenly began to expand. The cosmos was born, at first very small, and then growing ever larger up to the present day. This is called cosmic expansion. Everything I just described is summed up in what's known as the Big Bang Theory. It's called a theory because no one was there to witness it live, and it's pretty much impossible to prove events that happened almost 14 billion years ago with absolute certainty. But all the evidence points to it, and among cosmologists, this theory is by far the prevailing view. After all, we can observe without a doubt that the cosmos is currently expanding and that almost all galaxies are moving away from each other. If everything is expanding, then it must have started from a single point at some time. So that's a very, very strong piece of evidence for the Big Bang. But still, a few questions come up now. What was there before the Big Bang? What is next to space? And what exactly is at the edge? Does the universe even have an edge, or is the universe actually infinite? But then, what is it expanding into? I'm already getting cosmic headaches. Let's first clarify the question of whether the universe even has an edge. And then we'll see if we can actually see it. The problem with our idea of the universe is that we are three-dimensional beings. So we always imagine the expanding cosmos like a soccer ball that's being pumped up more and more. But the cosmos actually has at least 4 dimensions. Some cosmologists even assume there are more than 10 dimensions, and that simply goes beyond our caveman brains. One way to think about it, though, is to imagine the universe as a finite, curved surface, similar to the surface of a balloon. An ant walking on the surface of the balloon could go in any direction and would still never reach an edge. But our universe isn't a three-dimensional balloon, it's a multidimensional space-time balloon, and that's why, even though it's finite, it could have no visible edge. And we are like clueless ants, exploring the cosmic balloon, never able to grasp its end, blinded by our own limitations. I should become a poet. Some cosmologists have taken this idea of the infinite balloon a bit further and concluded that the universe is probably more like a donut. This concept of a multidimensional donut is also called the Poincare donut, named after the French mathematician Henri Donat. Just kidding. Of course, his name was Henri Poincare. He formulated the Poincare conjecture, which cosmologists have used as the basis for the donut universe. The idea behind the theory is that the universe could be curved in such a way that it bends back onto itself, similar to the surface of a donut. So space would not simply be flat and extended, but would curve in a way that is anchored in higher dimensions. A donut universe would be finite, but without a clear edge. It would have to have a limited extent, but this boundary would exist in a way that's almost impossible for us three-dimensional beings to grasp. And that's the key point about the donut universe. In contrast to most other cosmological theories, which see the universe as more of an endlessly extending pancake, according to the donut theory it's much, much smaller than previously thought and clearly finite, even if the end can't really be grasped. And of course, I didn't just introduce this theory so I could eat a donut in this video, although that was definitely one of the reasons. Multidimensional spacetime donut. No, this theory actually seems quite realistic based on some observations. To check whether the cosmos is a donut, you could look to see if it repeats itself in certain places. Just imagine, you start out at this point in the cosmos and eventually you end up right back at the same spot. That would be proof that the universe must be a multidimensional donut. Unfortunately, it would probably take quite a long time to run through the entire universe, and most scientists aren't really up for that. That's why they use telescopes to look for recurring elements in the cosmos. Unfortunately, in this gigantic universe, that's even harder than the famous search for a needle in a haystack. But conveniently, you can look back to a point when the universe was still very, very small. This means you can literally shrink the haystack you have to search through. Because every look into the sky is a look back in time. You see the objects as they looked when the light first set out on its journey. For example, you always see the sun as it looked 8 minutes and 20 seconds ago, because that's how long its light takes to reach Earth. Astrophysicists can look much, much further back, all the way to a point when the universe was only a few 100,000 years old. About 380,000 years ago, the universe became transparent. That means that suddenly radiation was emitted, more precisely, cosmic microwave radiation. Up to that moment, we can look back and see a gigantic wall of this very microwave radiation surrounding us everywhere. This is called the cosmic background radiation. Since the universe was much smaller back then than it is today, it's much more practical for cosmologists to examine this cosmic background radiation for recurring patterns in order to find evidence for the donut. Because if this theory is correct, then the universe was already a multidimensional topological donut 380,000 years after the Big Bang, just much, much smaller. A cosmological mini-donut. And that's exactly what a research team led by Thomas Butchard from the University of Lyon did, and they came up with truly surprising results. They examined the cosmic background radiation, CMB for short, which stands for cosmic microwave background, for large-scale irregularities, especially temperature irregularities. The hypothesis was that if one or more dimensions in our universe looped back on themselves like a donut, these irregularities couldn't be larger than the distance between the points where the universe reconnects with itself. Thomas Butchard puts it this way: in an infinite space, the fluctuations in the temperature of the CMB radiation exist on all scales. But if space is finite, then those wavelengths that are larger than the size of the space are missing. Or, put scientifically, if the universe is a donut, it can't be a pancake. But even if, like me, you think about donuts very often, it's still very, very hard to imagine, admittedly, because a multidimensional donut simply goes beyond what our little brains can grasp. But to put it simply, if the cosmos repeats itself in a loopy way at several points, there should be fewer irregularities in the temperature distribution, for example. And in fact, the studies by Thomas Butchard and his team have shown exactly that. He says, "We find a much better match with the observed fluctuations compared to the cosmological standard model, which is assumed to be infinite." The answer from our work is clear. The finite universe fits the observations better than the infinite model. So let's work with the donut universe hypothesis for a moment. The donut has an edge. So we should be able to see it somehow, right? Unfortunately, probably not, because this edge would likely be beyond our observable horizon. The observable horizon is the maximum distance that light could have traveled since the Big Bang, and which we can therefore see from Earth with telescopes. Everything that lies beyond this observable horizon is invisible to us, because the light hasn't had enough time to reach us yet. And how incredible is the thought that there are vast parts of the cosmos that we can't even begin to imagine. It's a bit like being on a ship and already seeing a huge expanse of ocean around you. But beyond the curve of the Earth, the whole rest still awaits you, which you can only see once you sail past the horizon. So, we are sailors on a sea of stars, and what we know is a drop, while what we don't know is an ocean. Okay, last attempt at poetry for today, I promise. But it's very likely that the light from the edge will never reach Earth, not even in the distant future, because the cosmos doesn't stick to its own rules. On large scales, it expands faster than the speed of light. Suppose two galaxies in opposite directions in the sky are 20 billion light-years apart. At the current rate of expansion of the universe, their distance would increase by 0.007% in a million years, which equals 1.4 million light-years. 1.4 million light-years in a million years. Obviously faster than light. By the way, this wouldn't make Einstein roll over in his grave, because he wouldn't mind. His cosmic speed limit only applies to the movement of physical objects through space from one point in the universe to another. In general, the expansion of space has nothing to do with the movement of objects within space and is in no way limited by the speed of light. So physics can breathe easy, but we can't. Because that means that information from the edge of the cosmos will never reach us, since it moves more slowly than the cosmos is expanding. Crazy, right? These cosmological questions make even the most brilliant physicists scratch their heads. NASA and other research institutions have made all sorts of other discoveries in recent years that bring us closer to understanding the edge of the cosmos. One of the most spectacular findings concerns the largest structure in the universe, the cosmic web. And here, astronomers have discovered something completely unexpected. Even when compared to the size of our solar system, we humans are absolutely tiny. The edge of the Oort cloud, the gravitational boundary of our solar system, is more than a light year away. And that's just our solar system, our cosmic home. The Milky Way, our galaxy, is, according to recent estimates, over 200,000 light-years across. And then, besides the Milky Way, there are up to 1 trillion other galaxies, and the universe as a whole is estimated to be about 93 billion light-years in size. Oh God, now I really feel small and insignificant. All of this is unimaginable, I know, but it gets even more incredible. The overall structure of the universe can be represented as the so-called cosmic web. You can see it here right now. And I promise, this isn't a photo of the carpet I haven't washed in 10 years. What we're seeing here are the matter structures of the cosmos packed together into filaments. These filaments are made up of all the cosmic stuff we know: nebulae, galaxies, galaxy clusters. We're also sitting on one of these filaments right now, in the Milky Way. So everyone wave and say cheese, this is the biggest group photo in history. Ah damn, I had my eyes closed in the photo. But the cosmic web doesn't just show filaments, it also contains the mysterious voids. These are gigantic empty regions of the cosmos between the filaments. So we can see that matter isn't distributed completely evenly throughout the universe. Alongside huge overdense regions made up of galaxy clusters, there are also vast cosmic areas where, basically, there's nothing at all. Sure, here and there you'll find a galaxy floating around even in a void, but for the most part, it's just like what's between some people's ears, nothing. So this is the largest scale structure in the cosmos, the cosmic web, made up of filaments and voids. And as if that weren't bizarre enough, scientists have now managed to detect magnetism in the cosmic web. The researcher involved, Dr. Tessa Wernstrom, says magnetic fields permeate the universe, from planets and stars all the way to the largest gaps between galaxies. Many aspects of cosmic magnetism are still not fully understood, especially on the scales seen in the cosmic web. Okay, so the cosmic web is magnetic, and we tiny primates on planet Earth can measure and map that. One step at a time. What exactly did the researchers do? They used all sorts of data and radio maps from sky surveys like the Global Magneto-Ionic Medium Survey, which were collected using radio telescopes such as the Murchison Wide Field Array in Australia, among others. With radio telescopes, you can map the entire sky in the radio spectrum and see where the highest density of radio emissions is found. The researchers then overlaid this data on the distribution of radio emissions in space with the simulated structure of the cosmic web, and bam! The final result seemed to confirm one of the most exciting cosmic hypotheses. It has long been suspected that when cosmic matter merges into the filaments, shock waves of unimaginable magnitude are generated. These shock waves emit radio emissions, which theoretically cause the cosmic web to glow in the radio spectrum. But this could never be clearly proven, because these signals are so weak. Until now. Because that's exactly what researchers have now achieved, they've been able to detect the radio glow of the cosmic web. When they gradually overlaid the radio mapping of the cosmos onto the simulated structure of the cosmic web, it was a perfect match. So, basically, it's astronomical detective work. And the processes in the large structures of the cosmos have, and now listen closely, been caught in the web by astronomers. Sorry for those jokes. By the way, the amateur astronomers among you know what the technique is called that the researchers used when they overlaid the radio images. Stacking. Only this time, it's on a truly universal scale. I know the whole topic is pretty complicated, so I'll put it a bit more simply for you. Not that I think you're dumb or anything. The researchers recorded radio emissions that originate from the shock waves traveling through the cosmic web, which in turn are created when large structures of matter collide. And this is the very first observational evidence that accelerated particles in the form of these shock waves are at work in the universe. Or as Dr. Tessa Wernstrom puts it, in the past, We've only ever observed these radio shockwaves directly during collisions between galaxy clusters. However, we believe that they also exist in the cosmic filaments. So the largest structure in the cosmos is being shaken by powerful radio shockwaves. Once again, that's a thought that really goes beyond what the human imagination can grasp, isn't it? So far, so good, but some of you are probably already wondering what this radio glow has to do with the magnetism of the cosmic web. A whole lot. Just imagine you're a subatomic particle, in this case, an electron, so a negatively charged particle, and you're cruising casually through the cosmic web, thinking about that attractive proton that's been smiling at you for days. Suddenly, you're steered onto a fixed path and become part of a kind of current. What just happened? The magnetic field of the cosmic web has caught you. The radio waves in the cosmic web are mainly produced when charged particles like electrons are accelerated in magnetic fields. So the magnetic fields in the cosmic web act as accelerators, steering the electrons onto spiral paths from which the radio emission is then radiated. This means that by observing the radio waves, astronomers can map the magnetic fields of the cosmic web and measure their strength and orientation. This, in turn, helps to better understand the structure of the cosmic web and its interactions with galaxies and galaxy clusters. Okay, I can already hear some of you asking, why is this weird guy from the internet telling me all this? The whole thing isn't as abstract as it sounds and actually has very practical effects on us as well. The formation of galaxies, their grouping into galaxy clusters, all of that is governed by shockwaves and the magnetic pathways of the cosmic web. These completely abstract processes in the largest structure of the universe are ultimately responsible for the fact that our Milky Way formed exactly the way it did. Because thanks to some magnetic pathway in the cosmic web, at some point in the universe, in some filament, exactly the right amount of hydrogen clumped together to eventually form the billions of stars that make up the Milky Way. You're now sitting at home in front of your computer, watching this video, which, by the way, you were just about to give a like to, and all of that is only because of the cosmic web. Cravey. You can also tell what a big deal we're onto here by the fact that the largest structure in the cosmos looks just like a Borg cube from Star Trek. Could that be a coincidence? Definitely not. It's incredible that this gigantic cosmic framework is crisscrossed by shockwaves. But that automatically raises a question. How are we actually able to look so far to the edge, or rather, into the past of the universe? Shouldn't that be completely impossible? And here we encounter one of the biggest problems in cosmology, the so-called horizon problem. Hold on tight, folks. This is going to give you a cosmological existential crisis. Immediately after the Big Bang, about 13.8 billion years ago, the universe was extremely hot and dense. In this primordial state, matter and radiation were so tightly bound together that the universe was opaque, much like the surface of a star today. But as the universe expanded, it cooled down. After about 380,000 years, the temperature had dropped enough for electrons and protons to combine into neutral atoms. This transition from an opaque plasma to a transparent universe is called the era of recombination. During this era, the cosmic microwave background was created. The photons, which had previously been scattered by the dense matter, could now travel freely through space. These photons now make up the CMB, which we can observe with modern telescopes. They permeate the entire universe and carry information about the earliest moments of its history. Since every look into space is a look into the past, we can actually look back all the way to the moment when the universe became transparent. So, astronomy is really just another word for time travel. That's one of the reasons why I find this science so fascinating. But now, some of you might be wondering, why is it called microwave, anyway? The temperature of the cosmic microwave background is currently about -270.45 degrees. This low temperature makes the CMB a form of electromagnetic radiation in the microwave range. With highly precise instruments, astronomers can measure tiny temperature fluctuations in the CMB, which point to minute differences in the density and distribution of matter in the early cosmos. So, by studying the CMB, we learn more about the early universe and why the cosmos developed the way it did. Astrophysicists also sometimes look for anomalies and dents in the CMB to perhaps find the effects of other universes within a multiverse. So you see, the CMB is the key to the greatest cosmic mysteries of all. Alright, now you might say, peace, joy, and pancakes. We study the CMB and its fluctuations, and then we know everything there is to know and can go home. Unfortunately, it's not that simple. The CMB holds plenty of mysteries, and the biggest and strangest of them is probably the horizon problem, which can be stated as follows. Why does the universe appear so homogeneous and isotropic when we look in different directions, even though certain regions of the universe have never interacted with each other? The fact that the universe is homogeneous and isotropic is called the cosmological principle. Homogeneous means that, to an observer, it always appears the same regardless of their position in space. Isotropic means that, to the observer, it always appears the same regardless of the direction in which they look. This principle applies to the very largest scales. This here is the cosmic web, the large-scale structure of the universe that you would probably see if you could zoom out far enough. If you're religious, you might say this is the map on which God plays with the universe. The galaxies are arranged along these brighter filaments. Between the filaments, there are huge empty regions called voids. Well, on this very large scale, the universe is extremely uniform. A uniform purple carpet of lint that probably really needs a good cleaning. But this uniformity can't really be explained, because since the Big Bang, not all regions of the cosmos have interacted with each other and thus could not have evened out. This is the horizon problem. Before we dive into possible solutions, pause the video for a moment and write your ideas in the comments. What is the answer to the horizon problem? How did space become so uniform? I'm really excited to hear your creative ideas and hope we can get an interesting discussion going in the comments. To understand the horizon problem even better, let's take a look at the expansion of the universe since the Big Bang. When we look up at the sky from Earth, we see light that has traveled to us from distant galaxies and celestial bodies. This light has traveled through space for a duration equal to the time that has passed since it was emitted. So far, so clear. According to the rules of relativity, nothing can travel faster than light in a vacuum, which means that the light we receive today potentially marks the boundaries of the observable universe. But here's the thing. The problem arises when we look at the temperature and matter distribution of the cosmic microwave background. Although this distribution appears to be homogeneous, the puzzle is that different regions of the universe we observe have never interacted with each other. For example, light from one end of the observable universe could never have reached the other end, because the distance is too great to have been crossed during the entire age of the cosmos. After all, the universe is only 13.8 billion years old. But the visible universe is at least 93 billion light-years in diameter. And yet, all cosmic regions seem to have similar properties. It's like you have a gigantic glass, tonic at the bottom, and you pour the gin in on top. And even though, according to the laws of physics, it should be impossible for the gin to have already mixed with the tonic, the cocktail is already perfectly blended and ready to drink. Somehow, astronomy always makes me crave a gin and tonic. I don't know why, either. How can we solve the horizon problem? There are a few ideas. One of the most prominent is the theory of inflation, which was proposed by Alan Guth in the 1980s. This theory postulates that the universe underwent a phase of extreme inflationary expansion shortly after the Big Bang. This allowed distant regions of the universe to come into contact and reach a homogeneous state. The theory of inflation not only explains the horizon problem, but also provides explanations for other observations, such as the observed flatness of the cosmos and the absence of magnetic monopoles in the universe. On the other hand, it seems a bit arbitrary to simply assume such an inflationary expansion just because it conveniently fits our observations. In my opinion, a somewhat more elegant solution is the cyclic universe. According to this idea, the universe exists in an endless cycle of expansion and contraction. During the contraction phase, distant regions of the cosmos come into contact and reach a state of thermal equilibrium. In the following expansion phase, the universe maintains this homogeneity, which could explain the observed uniformity of the cosmic microwave background. So, our gin and tonic is already mixed because it may have contracted and expanded an infinite number of times, which might be a reason not to drink it anymore, since it would be pretty stale by now. Then there's also the idea that the speed of light isn't fixed, but that it was variable in the early cosmos, shortly after the Big Bang, and that light was so fast that all regions of the cosmos could actually come into contact with each other. But there's not much evidence supporting a variability of the maximum speed, c. And that would really open Pandora's box, because we'd be tampering with the very constants of the laws of nature. So, what is the most likely solution to the horizon problem? Now that we've discussed several theories, let me know in the comments which one convinces you the most, or if maybe one of them even matches your own ideas. I'm really curious to see what. That's already almost unimaginable as it is. But now cosmologists have discovered something else that's even more frightening. Currently, the edge of the universe keeps moving further outward. The cosmos is expanding. But this expansion could just stop at any moment. The universe could start shrinking in the very next second. No joke, folks, these new findings are shocking. The term Big Bang was originally invented to ridicule the discoverer of the Big Bang theory, the Belgian physicist and priest Georges Lemaitre. Haha, you and your silly Big Bang, so cringe. But Georges Lemaitre was right, and today the Big Bang Theory is the gold standard in cosmology and is largely considered proven. But that last bit of certainty is still missing, since you simply can't look all the way back to the Big Bang. Maybe the James Webb Telescope, which was launched just a few weeks ago, will provide us with revolutionary insights about the early universe, since it can apparently look further back in time than ever before. But today, we're actually not talking about the beginning of the universe, but its end. That's a really big topic, because no one knows exactly how the universe will end. It was discovered quite some time ago that the expansion of the cosmos has been happening since the Big Bang, and strangely enough, it doesn't slow down the longer ago the Big Bang was. Instead, it's actually speeding up. The expansion is increasing. It's a strange thing, because the Big Bang happened 13.8 billion years ago, and the longer ago it was, the more its energy should decrease. That's why astrophysicists came up with a term for something that makes the cosmos expand faster. That term is dark energy. In short, nobody knows what dark energy is, but somehow it must exist, because something has to be causing the cosmos to expand faster. Science can be so simple. In any case, this rapid expansion could lead to several possible ends for the universe. The most likely scenario is that the cosmos will eventually become so large that it tears itself apart. That's called the Big Rip. Or alternatively, it could eventually become so gigantic that dark energy infiltrates even the tiniest structures, and the cosmos basically just freezes. That would be the Big Freeze. Both events, the Big Rip and the Big Freeze, would mean that the cosmos is then dead, which is of course a bit unpleasant, but until now it was assumed that this would only happen in the distant future. Until now, because now come the alarming news. The expansion of the cosmos could stop much sooner, in cosmic terms almost in the blink of an eye. Okay, maybe not quite that fast, but very soon. Cosmin Andrei from Princeton University in the USA has developed several theoretical models for the expansion of the universe. In his published results, which I've linked for you below the video, he says the universe is destined to go through a series of gentle transitions. The currently observed accelerated expansion will come to an end. Soon after, the expansion will come to a complete halt and the universe will enter a phase of slow contraction. The basis for this idea is mainly a thought experiment involving dark energy. Cosmin Andrei bases the paper on the idea that dark energy is not a constant present throughout the entire cosmos, but rather that the universe visible to us is indeed filled with dark energy, yet it is expanding into a kind of true vacuum without dark energy. At some point, the influence of dark energy becomes weaker and weaker, until eventually a counter-movement occurs, the expansion stops, and the universe begins to shrink. And if you take this as a possibility, you can calculate fairly precisely when this shrinking phase could begin. In the fastest calculated scenario, this could happen in just 6 to 5 million years. Now you might say, I don't care. 6 to 5 million years is such a long time, I won't be getting any pension from the state anyway. But from a cosmic perspective, that's an extremely short period of time. 6 to 5 million years ago was just when the mass extinction of the dinosaurs happened. But our planet is already between 4 and 5 billion years old. So 6 to 5 million years is an alarmingly short period for the reversal of cosmic expansion. And the question is, what impact would it have on us if the universe suddenly started shrinking instead of expanding? At first, not much of one. We would probably even have a hard time noticing it. Because most objects in deep space that are moving away from us are so far away that you would have to wait several million years to be able to prove any significant approach. And the objects that are closer to us, like our neighboring galaxy Andromeda, which you can see here, aren't actually expanding away from us at all, because their gravity is so strong that it overcomes the cosmic expansion. In the case of the Andromeda galaxy, this even means that we are moving toward each other, and in the distant future, it will merge with the Milky Way. So these nearby objects aren't suitable for confirming or disproving statements about cosmic expansion. If you think in very, very long-term terms, which never hurts, it wouldn't necessarily be to our disadvantage if the expansion were to reverse. Because right now, with every passing second, our chances of reaching very distant galaxies are dropping rapidly, since the farther away they expand from us, the harder it becomes to get there. And if this development were to reverse, then some galaxies might eventually come within our reach in a few 100 million years or so. Now, here's a completely wild train of thought from me. Suppose Cosmin Andrei's idea is correct and the cosmos could start shrinking within a short period of time. Couldn't that be an answer to the Fermi paradox? At least on an intergalactic scale? Just imagine an extremely advanced alien civilization in a faraway galaxy whose ideas and projects span very long periods of time. These aliens want to colonize a new galaxy, the Milky Way, take over all the planets there, and wipe out all rival intelligent life forms, which wouldn't be particularly nice. Now, these aliens do a simple calculation. We could set out right now with our gigantic fleet, but we'd have to use an unbelievable amount of resources to cover the distance. Or we could wait another 100 million years until the shrinking of the cosmos has automatically brought us much closer. Imagine, for example, you want to fly to Australia for vacation, but you know that next year, thanks to very rapid continental drift, Australia will be right outside your front door. Then you might say, okay, I'll just wait until next year to take my vacation, until Australia is right outside my door. I really need to come up with better analogies. In other words, the solution to the Fermi paradox on an intergalactic scale, that is, the reason why we haven't discovered any aliens from outside the Milky Way yet, could be that we're currently in an expansion phase of the cosmos, but aliens know that the contraction phase will start very soon, so they're simply waiting until then. It's a bit far-fetched, I know, but still interesting to think about. Feel free to write me in the comments what you think of my solution to the Fermi paradox. Now we've heard the term nothing many times throughout the video. There could be nothing besides the universe. The universe is expanding into nothingness. Before the Big Bang there was nothing. But what is nothing? Is nothing nothing, or is it something? Now things are really getting crazy. Ex nihilo nihil fit. Nothing comes from nothing. The ancient philosophers already knew this, but it is wrong, as we will see shortly. When I heard that sentence, the first thing that came to mind was the Big Bang. According to this generally accepted theory, the universe came into being in a singular event 13.8 billion years ago. Everything that exists today was squeezed into a tiny point, a singularity, and then suddenly everything began to expand and actually exist in the first place. According to the theory, there is no before the Big Bang. So you would have to say that something did indeed come from nothing, namely, the entire universe. But what does the situation look like today, now that everything somehow exists? Does nothing still exist? What is nothing, anyway? Before we go any further, write in the comments how you would define nothing. What is nothing? I'm really curious about your attempts to explain it, and I promise I'll reply to as many of them as possible. When we try to think about nothing, it somehow doesn't work. Even though it feels like a lot of people really make an effort to think about nothing. A lot of people would just say that nothing is simply a big black emptiness. But black isn't nothing either. Emptiness, maybe that's closer. What if we take an empty part of the universe? A piece of vacuum? Is there nothing in it then? Unfortunately, I have to disappoint you, folks. There's still not nothing in there, but rather quantum foam. Let's think again about our empty piece of the universe. First of all, we'd notice that even seemingly empty space is usually not a perfect vacuum. Even in the especially empty regions of the cosmos, between galaxies, there exists what's called intergalactic matter, so extremely thin collections of things like hydrogen and dust. Now I can hear some of you suggesting, then let's just suck out the hydrogen and dust. Then we'd have a perfect vacuum of nothing. Okay, so what would happen if scientists took our cosmic box and removed all the intergalactic stuff from it to create an ideal vacuum that's completely free of matter? Removing the matter would mean that energy would remain. Just like the energy from the sun can travel through empty space to reach Earth, heat from other parts of the cosmos would radiate into our vacuum. So the area wouldn't actually be truly empty. But we can solve that too. We simply cool the area down to the lowest possible temperature, absolute zero, so that it doesn't emit any energy at all. We also build walls around this corner of the universe so that no energy or radiation from outside can get in. Then, inside this cosmic box, there would be absolutely nothing at all. Right. Wrong. Unfortunately, quantum physics throws a wrench in our plans here. This is the branch of physics that deals with processes on the tiniest scales and often contradicts our apparent reality. Even though we vacuum sealed our box and cooled it to absolute zero, the quanta refused to stay idle. Even in such a supposedly perfect vacuum, tiny subatomic particles keep popping in and out of existence. It's a bit like the bubbles in bath foam when you're happily playing with your rubber duck. That's why it's called quantum foam. But before you go running a bath to become a quantum physics pro, let's first clarify exactly what that means. One of the most confusing of all quantum principles, and they're all confusing, is the Heisenberg uncertainty principle. And I don't mean the Heisenberg from Breaking Bad, but the physicist Werner Heisenberg. The Heisenberg uncertainty principle is commonly explained by saying that you can't perfectly measure, for example, both the position and the motion of a subatomic particle at the same time. When Heisenberg discovered this, some of his contemporaries probably said, "Then just get better equipment if your measurements are so imprecise, Werner." But the point is, these uncertainties can't be fixed by using better measuring devices. They're fundamental in nature. Subatomic particles simply can't be precisely determined for two different properties at the same time. To explain this with a very far-fetched analogy from the macroscopic world, if I were a subatomic particle, you couldn't precisely determine both my chocolate consumption and my waist circumference at the same time, which would be very advantageous for me. The principle also states that you can't measure the energy of something perfectly, and that the shorter the time you measure, the less accurate the measurement becomes. Taken to the extreme, this means that the measurement becomes infinitely imprecise if you try to make a measurement in a time span that's almost zero. But what does all of this have to do with our search for nothingness? A lot. Because even if we just try to measure the amount of energy in our cosmic vacuum box, even if that energy is supposedly supposed to be zero because of the uncertainty principle, you still can't measure exactly zero. Sometimes, when you take the measurement, it turns out that the expected zero isn't actually zero. And as we've already established, that's not a measurement error, but a quantum physical property of reality. For short periods of time, the 0 point isn't always zero. Heisenberg prevents the existence of nothingness. Now you might say, so what? So the measured energy just isn't always zero. But somehow, there's still nothing in that vacuum, right? Don't say that, folks, because that'll make Albert Einstein turn over in his grave. Einstein's famous equation E = mc² says that energy is matter and vice versa. Combined with quantum theory, this means that space in a place that's supposedly completely empty and without energy can briefly fluctuate to an energy that's not zero. And this temporary energy can turn into matter, into particles. Put more simply, if, according to quantum physics, little bubbles of energy suddenly pop up in our quantum foam, then we potentially also have matter, since according to Einstein, energy and matter are interchangeable. So the apparent nothingness in seemingly empty space isn't really nothing at all. The supposed nothingness is actually more like a pulsing place where tiny subatomic particles appear and disappear, which also means that our entire existence is basically a bath in quantum foam. Nice. So, no need to shower ever again. One more thing for the real skeptics among you who are wondering if this can actually be proven. It can, through the Casimir effect. Imagine you place two metal plates inside a vacuum chamber. These plates are only 1 millimeter apart from each other. If the idea of quantum foam is correct, then the area around the plates is filled with an invisible flood of subatomic particles that blink in and out of existence. And that's exactly how it is. In 2001, scientists succeeded in proving the Casimir effect. The pressure created by quantum foam causes the plates to move. Quantum foam is real. So nothing is actually not nothing. Phew. I don't know about you, but my head is really buzzing. Probably because it's full of quantum foam. I hope these discoveries fascinated you as much as they did me. The cosmos is truly full of surprises, and every day we learn more about the mysterious structures at the edges of reality. Of course, I'll keep you updated here on the channel about all the latest findings on these cosmic phenomena. So, if you haven't already, hit the subscribe button now and don't forget to give this video a thumbs up. And speaking of mysterious signals and unexplained phenomena, in Antarctica, researchers recently received a signal that, according to the laws of physics, shouldn't even exist, and it comes straight from the ice. What's behind this mysterious phenomenon from the eternal ice? To hear the whole spectacular story, be sure to click on the video shown at the top right. It's really, really exciting. Otherwise, I'd say we'll see each other in the next video. Take care, everyone.